Taking a look at gas stoichiometry here. Gas stoichiometry uses volumes, temperatures, and pressures of gaseous reactants or products. Again, gaseous meaning their state must be gas. So, of gaseous reactants or products are involved in determining the quantities of other reactants. So, again, all this means is if I have something that is a gas, so X is a solid and Y is a gas, I can use gas stoich on anything with a gas state. So note, molar volume only depends on temperature and pressure. Therefore, if conditions are not standard, we need to use ideal gas law. So what this says is if I have STP, let's use this, STP or SATP conditions, I can use the molar volume, so VM. But if I have non-standard conditions, I have to use PV equals nRT to find moles. Remember, this is V over N. All right. Students are asked to experimentally determine what volume of carbon dioxide is released in the burning of 50 grams of methanol at SATP. So let's start with a chemical equation before we decide how this is gas stoich. So we are burning methanol. The formula for methanol is CH3OH, and it's a liquid. If I'm burning something, a general combustion equation is that it needs to burn with or react with oxygen to make CO2, which is a gas, and water, vapor, so a gas. We were given the mass of methanol, and we are asked what volume of carbon dioxide is produced. So I know that this is gas stoich and not solution stoich, again, because volume is present in solutions and gases, because they are talking about SATP conditions and there's no concentration involved. So we are going to, in general, convert mass to moles here. Switch from moles of methanol to moles of CO2 using our mole ratio. And then we're going to solve for V, probably in this case because I've got SATP, using molar volume. All right, I'm going to do this with formulas once, and then I'm going to use unit analysis as well. I'll show both. All right, so the first one, I need to convert mass to moles. So I'm going to use N is equal to little m over big M. And I'm going to have my 50 grams divided by the molar mass of methanol, which is, I'll write it up here, 32.05 grams per mole. All right, so we get 1.5601 moles, and that was of methanol. Again, we talk about methanol and moles of CO2, so it's really important to just stay clear on what you're talking about. So that was step one. Step two is to switch moles. So I'm going to take what I just calculated, 5601 moles of methanol, and I just realized we forgot to balance our chemical equation. So let's go back up and do that. All right. I have one carbon. So I'm going to need 2 of these. However, that gives me 4 oxygens, and there's 1 oxygen here. So back to this, I'm going to double this up. And that's going to give me 4 of these, 2 of these. 4 and 4 is 8, 6, 3. All right. Now that I've balanced my equation, we're actually ready to do our second step. So I took my moles of methanol that I'd calculated in step 1 above, but I need to cancel moles of methanol. So they need to go on the bottom of my mole ratio. And I'm interested in finding moles of CO2, so they go up top. The numbers that I put in here are the coefficients from our balanced chemical equation. So 2 over 2. Although we could reduce that to 1 over 1, I'm going to leave it as 2 over 2 every time, just because those are the numbers I actually have in my balanced chemical equation. Okay, so don't ever reduce your mole ratio. All right, so we're going to get the same number of moles, but of CO2. All right, last step here. We're going to use the molar volume. So Vm is equal to V over N. And I'm going to solve for the volume in this case. The molar volume of a gas at SATP is 24.8 liters per mole. So, plugging in what I know, V is equal to Vm times N. Vm is equal to, V was equal to 24.8 liters per mole times 1.5601 moles. All right, multiplying that out, I get 38.6895 liters. Now notice that I kept some extra significant digits along the way. I didn't just write however many I thought I needed at the end. So this has 2 significant figures, and I've kept some extra ones throughout my work. These were never my final answer. So I don't want to round too early, otherwise that could cause some errors in this answer. So don't round until the end, but don't write out every number from your calculator either. There has to be a happy medium. So to 2 significant digits, this is 39 liters. So as promised, I'm going to show this in unit analysis as well. For unit analysis, I'm going to start with the given number, and that was 50 grams. I need to cancel grams and find moles. This is my molar mass, so I'm going to put in my 32.05 grams per 1 mole, and grams cancel. This was moles of CH3CO or OH because this is the molar mass of methanol. I need to cancel moles of CH3OH and find moles of CO2. Notice that the process is the same. Find moles of our known. Switch to moles of our unknown. Solve the equation. So we're at switching moles, and this is our 2 over 2 again. Moles of CH3OH cancel, and I'm left with moles of CO2. That's not what I want for a final answer. So I need to cancel moles of CO2, and I'm looking for volume, which we measure in liters. Now, liters per mole is our molar volume in this case. So 24.8 liters per 1 mole, and moles of CO2 cancel. I'm left with liters. Multiplying all the way across the top, dividing by everything across the bottom multiplied in brackets, we get the same answer. So with molar volume, we can use unit analysis right to the end. If 275 grams of propane burns in a gas barbecue, what volume of oxygen measured at 30 degrees Celsius and 98.6 kPa is required for the reaction? So notice that these are non-standard conditions. So molar volume doesn't work here. All right, let's write out our equation and actually balance it to begin with here. So propane was C3H8, and propane is technically a gas to begin with. We just compress it into tanks into a liquid. All right, so we need 3 of these, 4 of these, and that gives us 5. We are given a mass of 275 grams of propane, and we are looking for the volume of oxygen. So my first step is to find moles. And to do that, I'm going to need the molar mass of propane. The molar mass is 44.11 grams per mole. Basically, anytime you write a mass, write out a molar mass for that compound. All right, we are looking at finding a volume of oxygen. This volume of oxygen is using gas stoichiometry, where it's not a concentration. And because I can't use molar volume, I'm going to list the information I know below. So I have the temperature, which is 30 degrees Celsius, and the pressure, which was 98.6 kPa. All right, so step 1 is to find moles of propane, switch to moles of oxygen is our second step, and then solve for V as our third step. So N is equal to little m over big M. 275 divided by 44.11 grams per mole. Again, I'll do this in both formulas and unit analysis, just so you can see. And I get 6.2344 moles, and that was of propane, so I should write that. Next step is to switch moles. So taking our just calculated moles of propane, and I need to cancel moles of propane and find moles of oxygen. This comes from our balanced chemical equation. There are 5 moles of oxygen required for every 1. Remember, a blank space is a 1. So multiplying that by 5, we get 31.1721 moles of oxygen. Again, I'm using the number in my calculator each time. I'm not using my rounded number. I'm not typing this back into my calculator. So use the value in your calculator each time to continue on your work, even if you are just writing out part of that decimal. That gives you your most accurate answer. All right, last step is to calculate the volume. Well, I now have moles. I have pressure, temperature, looking for volume. I also have R. Don't forget about this one. So 8.314 kPa, liters per mole, Kelvin. Because we don't have a molar volume here, we need to use PV equals nRT to solve for the volume. So volume is equal to nRT over P is what we'll use. Turning this into Kelvin, we add 273.15. That is 303.15 Kelvin then. So volume is equal to our number of moles that we calculated, 31.1721 moles, times our times temperature in Kelvin, divided by our pressure in kPa, which it already is. So times 8.314 times 303.15 divided by 98.6, I get a volume of 796.81 liters. Significant digits. There were 3 here, 3 in our temperature, and 3 in our pressure. So we should have 3 in our final answer. I'm going to round this to 797 liters then. So notice that we used a different formula to find volume in this case because we had non-standard conditions. It wasn't STP and it wasn't SATP. If you want to use unit analysis here, the trick is that you can only go so far as finding the number of moles, and then we need to stop and use this formula. So I'll show you what I mean. I'm going to take my given number, 275 grams, and I'm going to cancel grams and find moles. So 44.11 grams per 1 mole, and that was of propane. grams cancel. I need to cancel moles of C3H8, and I need to find moles of O2. Again, this is 5/1. Moles cancel, and I'm left with moles of oxygen. So at this point, I have to stop doing unit analysis to just get my moles, which would have been 31.1721, so that I can take that and put that into the PV equals nRT equation like step 3. So unit analysis only takes us through steps 1 and 2 in this case in non-standard gas stoichiometry conditions, and then we still have to just use a general formula. Some people try to use the units of R to cancel. I'm not going to show that, but it is possible. So you can use unit analysis. You just have to be very familiar and comfortable with canceling units. Okay, so we can use R in this position to cancel moles, and then that'll tell us where to put everything else. Okay, this example goes beyond because I usually do stoichiometry a little bit different throughout the year. So don't take a look at this yet. This is limiting and excess, and we're going to talk about that a little bit later. I forgot to update our homework to the Nelson textbook, so I'll make sure that that happens ASAP as well, so that you guys have a good record of what to practice.